Okay, well, I'm going to introduce myself. Well, most people here know me, but I'm Jorge. I work in Program C with Pressey on conservation planning. And, well, I've been working on a few topics related to land sea planning, marine conservation planning, and social aspects of conservation planning. But today I'm going to be presenting a case study, and I'm going to try to show you how ecological and conservation science can be used in real-world applications for marine planning. As everyone here is well aware of, overfishing and climate change are two major threats that are affecting marine biodiversity, but also the existing services that marine biodiversity provides to people. This is particularly relevant because millions of people, especially in coastal communities, are highly dependent on the marine resources provided, and particularly fisheries because they are a major source of protein and source of income. So in order to tackle these challenges, marine protected areas or marine reserves, in this case in particular, are a tool that has been widely used across the world to protect the marine biodiversity, just because of the values that it has, but also as a management tool for the fisheries, and as a way to increase the resilience of these marine systems to the potential changes associated with climate change. Over the past decade, systematic conservation planning has been probably the leading approach or framework that has been used to design these networks of these marine reserves across the world. And there's many aspects of it that are important to point out, but three key aspects that have been pointed out by the literature, not only in conservation planning, but in general, that will make marine reserves more efficient and more likely to be implemented and to benefit the people are these ones. The first one is to incorporate socioeconomic aspects, and I'm going to go into the details later. The second is that it's important to think or to undertake a network approach that considers connectivity. And third is that we need to definitely have an idea and consider as much as possible the potential effects of climate change and how this may affect our design. So in terms of socioeconomic considerations, as I mentioned, one of the key aspects that has been missing especially from highly advanced conservation planning exercise is that there's a poor consideration of the social aspects or the social dimensions to planning. One aspect of this is that there's usually a common use of very simplistic or an incomplete data sets to represent the different values that marine systems have for the coastal communities. An example of this is, for example, the use of area or number of boats to represent the fishing effort, and this used as a proxy of the cost that these marine reserves will have on the people. Another very important aspect, not necessarily related to the cost, is that the information that we usually gather is biased. And it's biased because of the different problems with getting the data from the stakeholders on which sites are important for them. So most of the time, we don't have a very clear and complete picture of where all this fishing, for example, is happening. The second and very important one is that we tend to group stakeholders we tend to see stakeholders as single groups. For example, even though there's a multiplicity of, for example, if you focus on fisheries, there's a multiplicity of different types of gears with different preferences and different needs. We tend to group them as features and then act accordingly to minimize the overall cost for all of them together. These are several problems. One of them is that it makes marine reserves less likely to be implemented. A third factor, which is critical, is that we're just starting to realize that if we only use the social information to identify the cost of marine reserves, we're missing the opportunity to develop plans that are actually achieving social and economic objectives. And there's an ongoing project led by Georgina Gernig, which is actually showing that the inclusion of this information, instead of using information as cost, use it as objectives, will likely benefit the design and the implementability of the reserve. And finally, in terms of the social aspects, is that most of the time we don't follow a very participatory process to inform our planning. And this is a major concern because most of the time we try to go present a model and try to sell it rather than involve people from the very beginning, from the outset on the project, to develop it along with all the relevant stakeholders. In terms of ecological connectivity, so if you think about connectivity as defined by the movement of the propagules or the larvae in more particular, and the adults between areas across the ocean seascapes, we know that these aspects have been identified as very critical when we identify marine reserves, because on one hand, they will improve the probability that populations will be sustained in the long term, and second, because if we think about, for example, processes of replenishment and basically buffering our marine design for disturbances such as overfishing or extreme climatic events, then connectivity becomes quite important, and literature has extensively shown this is the case. There's also many different studies, most of them are relatively recent, that are actually demonstrating that considering a network approach is important in the design of marine reserves. And what these studies have shown, in summary, is that this connectivity is relevant for two aspects. One is to maintain the populations within the network of marine reserves, so basically maintain the exchange in the network. And second, but also quite important in terms of the social aspects, that this connectivity will also have to consider the exporting of both adults and larvae into the fishing areas, which is obviously going to make it more implementable. And although there are a number of very interesting emerging tools and methods that are useful to incorporate explicitly aspects of connectivity in marine reserve design, there are so far still very limited applications. I mean, practical applications of all these tools and methods, and this is a major limitation. With regard to climate change, the literature has already also shown, and probably a bit more widely than the connectivity one, that there are many needs to adjust the design of the marine reserves or the networks of marine reserves to hamper conservation investments. Sorry, to avoid hampering conservation investment. What this means is that instead of trying to protect areas that are going to be anyway lost, for example, due to changes in the seascape because of climate change, we might be able to identify what these potential changes are and then act accordingly and modify our design to address these needs. The second is that it has been also shown that there's going to be a multitude of impacts. So climate change is going to have different aspects. Perhaps some of the most important in terms of marine reserve design are that there are going to be likely alterations in the disturbance regimes, so let's say cyclones or bleaching events. And obviously this will be important for marine design. And in other cases, there will be shifts in the species distribution, which is probably going to result in changes in the community compositions. So both aspects are quite critical to think about when designing reserves. These aspects are important, but another one that is just recently starting to be explored as well is that climate change is going to be also having some important effects on the connectivity of the system. And this is where the two topics that are the core of my presentation come together. We know that overall, or in general, the increases in the temperature are going to result, for example, or in many other aspects of climate change, are going to result in reductions in the dispersal capacity or in the dispersal distances or in the proximity of the ecosystems connected. So if we are to design marine reserves that are buffered against climate change, we need to think about how climate change will affect connectivity. And finally, and unfortunately, but understandably, these aspects haven't been implemented because they're actually quite difficult. And most of the time they have been implemented in terms of generic design principles such as bigger is better, replication, avoid putting in areas that are going to be trashed anyway, and all these things, which are really important and are really needed and we need to continue considering, but are not explicitly considering the spatial variations and the processes related to climate change. So, despite all these advances, there is a recognized gap between the research and the application of all these concepts. This is very common in terrestrial, but it's actually also happening in marine exercises. So, because of this, and just to reiterate, there has been a very limited application of or consideration for the social and economic dimensions of conservation planning, I mean in applied conservation planning, and also in terms of incorporating or implementing spatially explicit models of connectivity and climate change to the design of marine reserves. So given that by 2020, the countries around the world are expecting to have at least 10% of the coastal or the marine ecosystems protected under some form of management, and, and that this is going to result in an increased number of new marine protected areas or marine reserves, there is an urgent need to get practical guidance of how do we incorporate all these aspects into the reserve into marine reserves design. So to tackle this gap, this project aimed to develop a practical approach to designing networks of marine reserves that consider socioeconomic factors, ecological connectivity, and the effects of climate change. And I'm going to show you how we did this. The project has been undertaken in the Midriff Islands region in the Gulf of California, and this is in Mexico. The area has been previously identified as a high priority conservation area by many different exercises. In a study that we did in 2013, we saw that at least 7 marine planning exercises have identified the region with different levels of consistency as a high priority for conservation. The image there shows the number of overlapping priorities, but because we don't think that summing priorities will give us the answer to prioritizing, we think that a regional planning is required. This area is very important also in terms of fishing activity. Multiple artisanal, industrial, and recreational fisheries happen in this area, and that is represented by the number of overlaps or the relevance of the region. And unfortunately, despite the existence of some marine protected areas, sorry about the figure, but they're shown there, there has been a limited recovery of the populations and ecosystems that are protected under these areas. So this basically points to the need to do something more about it. And something more about it could be developing a network of no-take, strictly protected marine reserves. So this project was born because of the common concern of fishers, government agencies, and non-governmental organizations that have realized together that there is a problem both in terms of environment and socially, and that we need to tackle it. So to do this, Comunidad y Biodiversidad, which is this one here, a local NGO that has worked for many years in the Gulf of California, decided to address the challenge by gathering or assembling a group of academics, government agencies, and representatives of the fishing industry to see how we can better design the management of the region. Sorry, I forgot to mention. So this, as probably some of them are not familiar with it, but basically this is the core planning team, and the planning team has national and international agencies, national and international universities, and the participation of us is because we were invited to lead the prioritization process and to integrate basically all this information and propose a process that will help us to develop this network of marine reserves. We think that the approach is very strong for 3 main reasons. And this is one of the things that we decided from the onset of the project. We wanted the process to be highly participatory, interdisciplinary, and collaborative, so that the decision-making process is not only based on sound science, but also is the uptake of the process is good with the community. After discussions between the people part of this group, we decided we agreed on 4 general or broad planning goals. The first one regards representation, and we aim to represent key habitats and species associated with rocky reef systems. The reason why we focus on rocky reef systems is because of the association of species of high conservation concern and commercial value that are happening or are associated with these ecosystems. We also aim to achieve ecological connectivity by maintaining the recruitment of focal species within the network, and in particular, we focus on maintaining this connectivity through the larval dispersal. We also want to incorporate climate change, and so basically what we wanted to see is that the design was such that the potential changes associated with climate change were going to be not affecting the marine reserve substantially. And finally, but not less important, is that we wanted to follow an approach that also not only minimize the cost of the fisheries, but also ideally provided some benefits to the fishing. So it's not only a conservation plan. So what are the features that we targeted in this plan? So the first one and logical one is, as I said, we focused on some species associated with rocky reefs. And we gather information from multiplicity of sources, which were later validated by local and regional experts, including fishermen that have been working with community biodiversity for many years. This information mainly came from a multidisciplinary and participatory research project called PANGAS, which has been running for more than almost 10 years now. And this part of this information has been integrated into Datamares, which is a geographic information system for the Gulf of California, which also integrates another two major long-term monitoring processes. And finally, using national and international databases on species. Because, as in any planning exercise, the information was not covering all the planning region, and we couldn't have information on all the sites that are relevant for the planning, we decided to follow a modeling approach. We use Maxent, which is a commonly used tool or software that is to develop species distribution models based on presence-only data. And because the information that we had was of high quality, the models that resulted from this we think are good quality as well, and these were also, of course, sanctioned by local experts. So we created this for over 100 fish and 100 invertebrate species associated to these systems. We also updated information, the spatial information that was available from previous studies, but also based on remote sensing information and on local knowledge about those habitats that we consider to be most critical for the conservation of these features. So basically, of the species that are associated to rocky reefs. And so we come up with updated maps of rocky reefs, mangroves, seagrass, sargassum, and spawning aggregations. So this broad goal of representation had then to be translated into quantitative objectives. And the way we did this is we defined a percentage of the current distribution of these conservation features and set habitat or species targets that were relevant to the ecology of the species, but that were also individually assigned to each of the bioregions. This allowed for replication, which is one of the general principles to address, for example, climate change. The way we set up the habitat targets followed the method developed by Jonathan Kuhl and others in 2010, and it's based on the rarity and the exposure of habitats to threats. We use a log index rarity index because the distribution of these habitats was obviously not very homogeneous, and the amount of each habitat within the region was different. So this allows us to put the information together, and it basically assigned a minimum of a 10% target for any habitat, but could go up to 50% if the habitats were affected by many different threats. And this is, of course, this is not including fisheries, because we're not mixing fisheries with threats. And the second related to the rarity, or how abundant the system was in the marine region. The species targets were developed very similarly. The vulnerability was calculated in a different way based on trophic level, habitat breadth, and the range of depth. And we added an additional element, which was heterogeneity, which is basically a measure of how patchy the distribution of the species is within the system. We gathered some of this information from FishBait and other local databases. And finally, in terms of the spawning aggregations, we follow a very similar approach to the one that we follow for the habitats, but because of the relevance of these features in the seascape, we decided to assign a base target of 50% as a minimum to be represented in each of the ecoregions of the planning domain. We know that, as I said, that socioeconomic considerations are critical for this, and the way we use two general criteria. The first one was, obviously, we want to minimize. It's not going to be possible to not have any impact on the communities. So we aim to minimize this cost as much as possible, and in this case to the fisheries, which were the major or pretty much the only stakeholder that is likely to be affected by this. And the second is we aim to distribute this cost as equitably as possible. It's been well studied now that if you just think about, as I said, of all the stakeholders as a single unit, it is likely that the cost and the benefits are not going to be distributed equally among the different stakeholders, and that might constrain the implementation potential of the marine reserve. To do this, we used, to tackle the aspect of the cost, we developed an opportunity cost layer. We use opportunity cost because, as I said, we had incomplete information and biased information on which are the areas that are most important, and also because of the potential changes in time of which areas can be used given the potential of the marine environment to provide, in this case, fish and invertebrates. The way we calculated opportunity cost, we followed what we consider to be best practice so far, which is a method developed by Vanessa Adams and others in 2011. And for each individual gear, we calculated the opportunity cost as a function of fish catch probability, abundance, biomass, and the market value. And then we summed the opportunity cost of of each gear and weighted these based on the number of fishes. There's different ways of addressing this aspect, but we decided to use number of fishes because that's the information that was available. Alternatives to doing this is to use, for example, vulnerability of species. So basically what this function will do would be to assign a cost that is more amenable to the different stakeholders that will be affected by the marine reserve design. And we did this using a bioeconomic model called Atlantis, which was originally developed for Australia, and that has been used also in the USA, which is basically a very complex model, which I'm not going to go into describing because it's actually quite hard to understand itself. But it incorporates relevant aspects to this at the seascape level, and there's a very good model for the Northern Gulf of California. So we decided to use this information to calculate the opportunity cost of the region. So before jumping into how we implemented connectivity and climate change in our design, I'm just going to briefly summarize how we define the management or the conservation problem, because the way we define a problem is critical on the way that you are going to be prioritizing or designing your marine reserves. So the optimization approach that we follow was what we call the minimum set problem, which in very simple words is minimizing the cost, in this case of the whole network of marine reserves, subject to achieving defined objectives. In this case, the objectives that I discussed earlier in terms of habitat representation and blah, blah, blah. So because we didn't want to buy into what particular approach, and we need to see what are the benefits or the pros and cons of different, we used three methods and we compared them in the values. The first one was a typical conservation planning approach using Markson, which is a commonly used conservation planning tool that basically helps us to identify systems of reserves that efficiently meet the conservation objectives while minimizing the cost. The way we added connectivity is going to be explained a bit later, but just for the sake of clarity here, I'm going to mention that the way we addressed this one was to add a conservation, an objective specifically related to the value of connectivity of planning units. The second, and this is related mostly to the incorporation of social aspects, socioeconomic aspects into the design. We are trying Markson with zones, which is a relative of Markson, but that allows to the identification of multiple zones who are prioritizing, and that allows to the use of different and multiple socioeconomic costs. In this way, we were able to set specifically fishery-specific objectives that could be achieved, and instead of minimizing the cost, we will basically try to achieve social and conservation objectives at the same time. And finally, we're using another relative of the Markson family, which is Markon or Markson with connectivity, which is a software that basically allows to develop networks of connected marine reserves. And that is what this software was made of. And what it allows is to clump or to select areas that are not necessarily adjacent to each other, but that are connected ecologically, for example. We use a uniform 1 square kilometer grid as our planning units, and we decided to include the coastal ecosystems because of the relevance of these ecosystems to sustain the marine populations. Today I'm just going to focus on the first bit because this is an ongoing process, and because otherwise I would be here for probably another 3 hours. So how did we incorporate functional connectivity? So we we decided to use a focal species approach, and we chose these two species. The first one is the leopard grouper, and the second one is rock scallop, so one fish and one invertebrate. The reason why we chose these two to represent the connectivity or to account for connectivity in the network is because they have some differences in the patterns of connectivity. So one, they have different planktonic larval duration, which obviously will affect the connectivity. And second, they spawn at a different time of the year. So the expected influence of the currents will be different at different times of the year. Both are of economic importance, so both are species of conservation concern as well. So how do we do this? Again, I'm not going to go into the details, but what we did is we developed a larval dispersal model that was supported by a dynamic oceanographic model that was validated by empirical data. And this is a bit of a mouthful. But what this really means is that we don't, some of the plants that at least I've seen have tried to use oceanographic models to predict whether, for example, the larvae will be, and based on that calculate the connectivity matrix on how things are connected in the landscape. But this hasn't been proven. So this hasn't been validated by empirical data. So what we had for these two species was areas that we know are areas of spawning aggregations, and we have information on the genetics of the species and on the population. So we could actually see that the model, that what the oceanographic and larval dispersal model was predicting was actually congruent with the results of the empirical data in terms of the genetics. So after this, and this is obviously a long-term study that has been ongoing for quite a few years, we found, and not surprisingly, that there was a strong connectivity, a strong asymmetry in the way that the planning units, or in this case, the connectivity units were connected. This we knew from previous studies that there was a strong cyclonic general circulation pattern of the area, but we didn't quite know how that was going to be affecting the connectivity. And so, based on the modeling of the larval connectivity, we found that some areas are very strongly connected, some areas are connected to the north, some areas are connected to the south. In this case, the colors are showing the net direction of the movement of the larvae, and the thickness of the lines is representing the probability that the larvae will go from one side to the other. And so this is the information that we're using for a study. So we decided, based on this information, we decided to follow what is called a graph theoretic approach, or an approach based on network metrics, and we basically set objectives based on the importance of planning units. So depending where the planning unit was and how it was connected to the other one, it was going to have a more or less, a higher or a lower importance if it was, for example, identified as a stepping stone. What this means is, if I have a unit that has a high, for example, centrality, and it's very important to keep the full network connected, then it's acting some sort of a stepping stone. So removing this marine reserve of this area from the network will have a large or more important consequence than removing, for example, a more peripheral planning unit. And peripheral, I'm talking about in terms of networks. So I don't intend you to read this, but as I mentioned, climate change is probably going to have very different effects on the connectivity of the system. And while this could be affecting both the structural and the functional connectivity of the system, we decided to focus on one particular aspect for which we have information and which we think it was relevant. So we thought that we should basically focus on the rising ocean temperatures and how that affected the potential main dispersal as mediated by the pelagical larval duration. And what this means is basically we expect that increasing temperatures in the ocean will likely result in a reduced planktonic larval duration, which eventually will be reflected in the patterns of connectivity. And how does this look before going there. So what we did is we calculated the connectivity matrix for each species and for each planning unit. And so this is basically how it looks. So we have the connectivity units here and the connectivity units here. And as you can see, the values on this side of the matrix is different to this one, which means that there is a strong asymmetry in the movement of the larvae. And this is the information that was used to feed into the model. For the leopard grouper, we decided to use betweenness centrality because that was the parameter that significantly explained the genetics of the system, while for the rock scallop it was the eigenvector centrality. So those were the criteria that we used and why we selected those. So we developed two climate change scenarios. The first one was without the increase in temperature, where we used the let's say, the standard PLD values of 28 and 21 days for the Mcleod rosacean, for the rock scallop and for the leopard grouper. And then we decided to have just one scenario for the sake of simplicity, but we were likely to explore more, which was predicted 2 degrees increase in sea surface temperature, which eventually will result in a reduced PLD down to 21 and 14 days. So, as I said, we set two objectives, one for each species that will represent the importance of planning units in terms of maintaining the overall connectivity of the network, and we set up targets to include these units within the system. And this is more or less how it looks. So this is an example for 3 different PLD values resulting from the larval dispersal model, and it's showing as you can see here, there are notable differences in the way basically in the areas that the larvae are expected to reach if you modify the PLD, which as predicted by the changes in sea surface temperature. So the way we implemented this in Marxen was we tried to identify the differences if we included connectivity or we didn't, and if we included connectivity plus the climate change. So we basically defined 3 scenarios that we could compare and see how different this would look like. The first one was a typical Marxen approach, no connectivity, representation, goals only. The second one was representation plus connectivity, which was basic, as I mentioned, including planning units that were important because of their stepping stone role. And the third one was exactly the same as a second scenario, except that the PLD was reduced, and so the connectivity patterns were obviously going to be modified. Because probably, especially for people that are probably not familiar with Marxen, it's still a bit blurry what this means of using Marxen or using Marxen with connectivity means. I just thought about important to mention how this looks like. So the typical Marxen or Marxen with zones, the way the software works is that given the equal conditions in, for example, the distribution of the biodiversity or the conservation features of interest, if, for example, we require to protect 2 planning units to conserve the things that are of interest, the way Marxen works is it basically can choose this one or this one. And the reason why it chooses those 2 and not 2 and 4 is because usually what it's aimed to is to reduce the overall edge area and reduce to basically to clump things to make it more implementable and to avoid risk. The way this works is probably not very useful because we know that planning unit 1 is not necessarily as connected to planning unit 4 as to planning 2, as it's visible from this hypothetical example. So in this case, what we did is we transformed this connectivity matrix into a value of these planning units, where, for example, planning unit 1 has a very strong centrality importance, and it's a critical stepping stone, and is strongly connected to planning unit 2. So in this case, by using the approach that we follow, we assume that Marxen was going to select planning unit 1 and 2 all the time instead of planning unit 1 and 4, because those are the ones that have high values for connectivity. What we're planning to do, but we're still working on it, is to actually use Marxen with connectivity so that we can do this explicitly. So instead of assigning a specific objective to select areas that have high centrality, we're going to forget about including an additional objective, and we're going to try to clump things instead of the typical Marxen way, which is basically considering clumping units because they are adjacent, clumping units because they are actually connected, in this case, based on larval dispersal. So we think that the result is going to be the same. So Marxen is going to go on, going to try to select these 2 planning units because they're ecologically connected. And so in the end, when we finally make the comparison between these 2 scenarios, I'll be able to tell you if that is the case. So this is what we found. This is just an example of the first typical scenario with no connectivity, no climate change. And when the managers saw this first run, they thought, it looks reasonably all right, and I think that could be solved, and it looks like something that could be implementable, blah, blah. But there was something that was not very good and that we couldn't figure out what was happening. And so to explain what this is, I'm going to show this different output of Marxen. So the first one is just a network that achieves the objectives of representation, basically. The second one is it's a product that which is called selection frequency, which is basically showing the number of times that a planning unit is selected. And the more times it is selected, it means that the planning unit is probably going to be more important to achieving the conservation goals overall. As you can see, but especially for people that have worked with Marxen, there's a potential problem here. There's a lot of areas that are never selected, right? There's a lot of areas that are gray all the time. And this basically, in practical terms, means that the flexibility of our approach is being constrained by something. And it is very likely that the major constraint in this case, it's not related to connectivity or anything else, but especially because this one doesn't have connectivity, but to the use of the coarser resolution cost layer, opportunity cost, which was developed by Atlantis. So we have a very good model that is actually really good to predicting the opportunity cost, but it's a bit coarse. So, what happened when we compare the things? I know this is a bit small, but a general inspection of these processes, and just to make sure, so this is the scenario 1, again, the best scenario, the best configuration possible, and the selection frequency. Scenario 2, which is connectivity. Scenario 3, which is connectivity and climate change. So there are some differences, but they're not really marked. And the reason why, again, I said this could be happening is because we're being constrained. So unfortunately, so far, although this is, as I said, it's an ongoing process, we are not able to identify how important the inclusion of the additional connectivity objective in the prioritization process is acting. So this is something that we continue working on, and we'll hopefully be able to have something more final in the near future. So, first step to work on, and I'm working on this during my weekends. So, and I don't have too much of a weekend, so this might take some time. But we're trying to revise the opportunity cost using a finer scale spatial information on species abundance and biomass that has been developed as I speak. 2, as I said, we are going to develop a scenario that is setting explicit socioeconomic objectives, basically to retain fishing areas. We don't know how different this is going to be to the typical Marxen scenarios because we haven't tested it. But we think that using this approach will be likely to have a network that is going to be more amenable to implementation, that is going to be more acceptable for the users, and it's going to be more equitable in the distribution of the impacts, both the positive and the negative. Also, as we speak, there's an ongoing extensive engagement process with fishermen along the main fishing villages and communities in the region to collect more information about what are the preferences, what are the limitations, what are the constraints that communities have and will be facing if a network of these characteristics was implemented. So this is very important because, as I said from the very beginning, the process, what we're developing here is a process of how to design using the best science possible, but it's not developing a product that I will go and deliver to the communities. The plan is being led by this local NGO, and the idea is that they will go with this process in hand, and has been shown to be possible in other exercises like the ones that TNC has undertaken in the Solomon Islands. You can actually go with your computer, run the things. Oh, we don't like it. I think this is not wrong. We run analysis. So basically, an iterative process that will allow negotiation on the go, right? So this is what we're doing, and as part of the activities that I'm doing, and I'm going to be visiting Mexico in a few weeks' time, is to do some also training of local experts and local managers so that they can know how to run all these tools themselves, and then finally they can go, and in this process of I would call negotiation, but it's not negotiation, of development of the final plan, they will be able to do this themselves. And I won't have to be there, although it wouldn't be bad to be there. I just don't have the time. Then, again, missing thing, but we're working on it, is we're going to be working on the implementation of the connectivity using Marxen with connectivity. Hopefully we'll get something exciting about it. one thing we haven't done, but we think it's going to be important, at the moment we're integrating the objectives for the two focal species all together. So we don't really know how different they would look if we just use one or the other. This, from a scientific point of view, is quite important because sometimes you won't have information for more than one or two species. So we're going to try to do this for the two that we have, and there's another set of information for a crab species. And we'll try to compare how these different configurations are. And if they're very different, then we need to start thinking about what are the trade-offs and what are the benefits of using one or the other. So this is something that it's ongoing and we're thinking of doing. Of course, there are multiple opportunities for improving this, not only the design, but the general process of the way we are approaching the design of the marine reserve in the region. We know that in this case, and this is something that is probably, it was surprising for me the first time I knew about this. So the Gulf of California, the northern Gulf of California goes like that during the summer and goes like that during the winter, right? So this is a problem for connectivity because the pattern is going to be completely different. And while most of the conservation and especially the commercial valuable species are spawning during the cyclonic phase of the northern Gulf, there are species of conservation concern that are spawning during the winter. So that means that the connectivity that we're going to be planning for is not necessarily going to be the best. Unfortunately, we don't have these models validated by these other species. So there's going to be a trade-off. Should we try to model this based on the theory, or do we need to wait to get more information? Likely, we're not going to be able to wait because, as we speak, these areas are being degraded and are being overfished and are being affected, and this is affecting people. This was developed basically by translating these larger scale connectivity units into the smaller planning units. But we would like to run the oceanographic and larval dispersal model using our planning units. And this, for the people that have worked with ocean models, know that if you're working with 10, 20, 30 units in connectivity, it's fine. But if you have thousands or hundreds of these, then it's a completely different task. So this is a potential opportunity, but I'm not sure we're going to be able to do it on time. Other things is we're using those metrics because those were the ones, the centrality metrics that best explain the diversity, the genetic diversity in the region. But there are others, and we would like to perhaps use some approaches developed for example, from the social network analysis theory on how to develop a way to select the best network that is going to be giving us an overall whole of network connected marine reserve network. And then, as I said, our approach was focusing on stepping stones, but what happens with the sinks? So we know that the units, the metrics, the connectivity units, or the network metrics that we use are negatively correlated with the genetic diversity of these areas. And what this means is that some of these areas that are not going to be probably very central in connecting the different areas of the network might be receiving a lot of these larvae, and therefore they're likely to have a higher diversity. This is probably good in terms of potential for adaptation to climate change. So if one of the objectives of our planning study is to achieve the best way possible to account for climate change, then we probably need to think about how we're going to deal with these things, and we might just have to include them as well. So we might end up including everything. So just to finalize, we think that our process's main strength comes because, as I mentioned, it's a participative, collaborative, and exploratory in terms of all the things we're trying to assess alternatives, and that this will likely lead to implementation or more easy implementation. We think that our model can be a good way of show how the use of cutting-edge science can be used in applied planning exercises and in a real-world example of management environmental problems. As I said, there's many improvements. One that probably some people here have already started to think is how do we use some more complex things like metapopulation analysis to set specifically conservation targets to basically say, okay, I want this network to be able to, on the different climatic and use scenarios, to maintain a certain recruitment and maintain a certain number of export larvae into the fish areas, blah, blah, blah. And the only way to do this is to use more sophisticated tools, which at the moment are not available for the region. And some future research topics, perhaps just food for thought is what about integrating optimization and simulation models to assess the socioeconomic and ecological impacts of networks on the different scenarios. So if anyone has some ideas of how to integrate Marxen with Atlantis, I'll be more than happy to have a chat about that. And last but not least, there's a lot of people that have contributed to this project. This is the core team. Obviously, behind many of these people are all the people working on data processing and sale. And so this is just, again, to reiterate that this is a very, very collaborative process with a lot of people involved, and the role of each person and institution is quite important. So I would like to thank, and particularly to Jorge Torre, who's the leader of the project in Comunidad de Biodiversidad. So thank you very much. I'll be happy to take any questions if there's time.